This is one of these sea urchins. Would you believe that each one of these spines is a single crystal of high magnesium calcite? Actually, the spine is not solid calcite. It's precipitated by this animal in the form of a three-dimensional meshwork structure, as you can see in our photograph. These pores are only a few microns across, but in the living animal they're filled with soft connective tissue. The animal is able to take a brittle and easily broken material like calcite and to form parts of its skeleton, like the spine for example, with a phenomenally high strength-to-weight ratio. This spine is a natural example of what we call a composite material.
For business and industry, the Pennsylvania Technical Assistance Program presents Looking at Materials. Today, composites. Your host is Louis R. McCrite of the General Electric Space Sciences Laboratory.
Various eras of man's history have been named after the materials which were developed and discovered in those times. For example, the Stone Age, later the Iron Age and the Bronze Age. What might people call our age? They might very well call it the Composite Materials Age because of the great developments that are being made in these advanced materials nowadays. Here, for example, is a little replica of a sample that was buried in a time capsule at the New York World's Fair in 1964 to be dug up 5,000 years from now. It contains a sample of an advanced composite, in this case aluminum oxide whiskers, in aluminum metal. Well, you may wonder now, what are these advanced composite materials? There are several different things. For example, aluminum oxide whiskers, which are very, very strong, in fact the strongest materials known to man. They're boron fibers. Also silicon carbide and boron carbide can be made in a similar form. They're used in turn to reinforce a resin, such as this sample, or they could be used to reinforce a metal, such as this little bar of nickel. You may then wonder why the advantage in these materials, that is, what's new? Why are these fibers so much better than some of the others that you're more familiar with? And first, you're familiar with fiberglass plastic, I'm sure, such as in this fishing pole. But the advanced fibers offer a great deal of stiffness to weight ratio, which is very important to the designers of various advanced vehicles. For example, they primarily build their vehicles of aluminum. If we hang this weight on the aluminum bar, we see that it deflects a couple of inches. Now, if we were to make the same weight of bar into fiberglass plastic, we'd have this sample, and well, we see that a weight very greatly deflects that sample. If we take the same weight of boron epoxy, however, we find that it hardly deflects at all. Well, this looks so great that you now may wonder, well, why don't we make the whole beam or a whole sheet out of boron material or boron-like materials? The answer to that is rather simple, that first of all, it's very difficult to fabricate boron or similar materials into large sheets and beams. But even if we could, we would have trouble with the surface scratches and the notches that could cause catastrophic failure. However, if we make the materials into these fine filaments, we find that they're not only stronger, but that if a few of the filaments break, it doesn't really hurt the overall effects of the strength of a beam. If we look at these samples, for example, we see boron epoxy with bullet holes in it and fiberglass epoxy with a bullet hole in it. It's broken a few fibers, but overall it has not shattered the whole beam. Now, as you can well imagine, an aircraft designer, for example, is always striving to make larger airplanes and to reduce the non-essential weight of his aircraft in order that it can carry more payload or more fuel to permit longer range flights. The materials available to the designer govern the extent to which he can succeed in doing this. And unfortunately, the present materials that are primarily used are not really improving in their properties as fast as we would like to have them, and as fast as the demands on them would like them to be improved. So, as we can see in this chart, we must turn to composites. We've got aluminum, steel, and titanium all coming up onto a plateau of strength, in this case, to weight ratio over the last few years. Now, as we've developed composites since the early 40s, first of fiberglass plastic down in here, and later of the advanced composite material, we see that they're on the order of 3 times stronger and 3 times stiffer than the current materials. Now, in the past few years, the development of these advanced composite materials has progressed quite rapidly, and there's many prototype parts of aircraft already being flown. These parts are performing very well, and they're indicating that weight savings on the order of 25 to 50%, and in some cases even a little more, can be safely predicted. These current developments are based on substituting advanced composites for conventional materials, or in a few cases of combining the two approaches. For example, it is possible to take a metal tube, stiffen it with a layer of boron epoxy tape over the outside, make an overall combination that is much stronger and stiffer than either of those two materials by themselves would be. At present, the high cost of these composites is justified by their performance in certain critical applications. In the future, as the cost is reduced, however, one can expect to see them used in nearly entire helicopters and entire aircraft. At that time, we'll see the difference between our old model airplanes and new model airplanes, I think. For example, in our day, balsa wood strips and tissue paper were the common materials of construction for our model aircraft. Nowadays, our boys use various large plastic parts and simply glue them together to make their model airplanes. Real airplanes, I think, will also be made very much like this later model, of large pieces of composite fastened together with adhesives and with various resin materials. Now, what will that offer in the way of performance is shown in this chart, in which we compare the design of a large present aircraft made of conventional materials with what it might look like in the way of weight, performance, and so forth, made of composite materials. First, we have the opportunity to reduce the weight by half, keeping the payload and range the same and still only use a fifth as much fuel. Secondly, we could do the same job of reducing or increasing the payload by a factor of 2 if we keep the weight and the range the same, but we reduce the fuel load by half. Third, we could have the same weight, same payload, and same fuel load, but triple the range. Now, we've mentioned just a few of the uses of these composites. Later, we shall be describing in detail their application to helicopters, because this represents one of the first applications to justify the use of these materials in significant quantity. As their availability increases, however, and as more people learn how to design and fabricate them, their use may well extend all the way from sports equipment to high-speed trains to large industrial machinery and even bridges and buildings. But now let's dig just a little deeper to see how some of these fibers and some of these composite materials are fabricated as we visit Dr. Joseph Mullen of the General Electric Space Sciences Laboratory.
As we have heard, composites derive their most desirable structural characteristics from the basic reinforcing mechanism. This comes into play when high strength and high modulus filaments are encapsulated in a matrix material which is weaker and more flexible, such as plastic or ductile metal. Filaments themselves are much stronger than bulk quantities of the same material, and this is illustrated in a diagram. Here we have plotted strength as ordinate and 3 diameter ranges on the abscissa. 3 different classes of materials are represented here: metals, glass, and ceramics. Notice in each instance how the strength increases as the diameter decreases. This may seem puzzling at first, but we now know that very fine filaments have fewer point defects. And because these point defects are a critical source of weakness, that the very thin filaments will have much greater strength than filaments of larger diameter. Since the filaments are narrow compared to their length, they are in need of support. The matrix provides this support, and the filaments in turn provide strength to the matrix. Because of their very nature, filaments in a single layer must be aligned in a parallel arrangement. This is illustrated in the following figure. Here, strength is plotted against orientation angle. The reference direction is the axis of loading. Strength is maximum in the aligned condition where the filaments are parallel to the load direction, and as the filaments become more inclined to the axis of loading, the strength diminishes until finally, when the filaments are normal to the load direction, the strength is minimized. For this reason, composites have what are termed directional strength properties. And these directional strength properties can be tailored to fit specific applications. This is not all, however. The orientation of filaments also influences not only the strength, but the modulus. You will recall that modulus is a quantity which measures stiffness, and this was illustrated earlier by Mr. McCreight with the beam demonstration. In the simplest application, all filaments are aligned in a parallel arrangement. Here is a molded bar in which the filaments are exposed at one end. Continuous filaments of boron and silicon carbide in this configuration can reinforce plastics to strengths on the order of 200,000 pounds per square inch, depending on the number of filaments per unit volume and, of course, on the manner of loading. A cross-sectional view of such a composite would look something like this. Here we see boron filaments in an epoxy matrix. Notice that all the filaments are in N view because it is a cross-section. These filaments are continuous filaments, but it is also possible to reinforce a matrix material with discontinuous filaments. For example, the strength of an epoxy resin matrix has been increased 5-fold by putting whiskers, as shown in this cross-section, in an epoxy matrix. Notice the difference in geometry of the cross-sections for whiskers. The whiskers shown in this photograph were actually grown in this laboratory and are single crystals of aluminum oxide which have very high strength. They are grown in a furnace which looks like this in ceramic containers. The ceramic containers enter at this end of the furnace and are charged with aluminum. They pass along a conveyor, and during the process of passing through the furnace, the whiskers are grown. When they leave the furnace, the ceramic container filled with whiskers looks something like this. Whiskers grown in this manner must be separated and oriented into a nearly parallel arrangement before they can be used in a composite. One method of separating and orienting whiskers is called Aero Lutriation. As grown wool is placed in the bottom of this separation chamber and blasted by jets of air. The individual whiskers then travel up this column and are collected on a screen between two cones in the upper portion. A strand formed in this manner looks something like this. The difference in color, of course, is due to the fact that these whiskers have been metallized before placing them in the elutriator. This strand can then be infiltrated with matrix material to form a composite. Although the major area of interest in composites involves the use of resin matrix materials, a good deal of study has been devoted to improving the temperature characteristics, high strength temperature characteristics of metal matrix composites. At 900 degrees Fahrenheit, unreinforced aluminum has a strength of about 800 pounds per square inch. But by reinforcing it with 25% by volume of whiskers, the strength becomes as high as 65,000 pounds per square inch. And when it is reinforced with 45% by volume of boron filament, the strength can be as high as 100,000 pounds per square inch. It should be pointed out here, however, that uncoated boron filaments are degraded after prolonged periods at these temperatures, whereas the alumina whiskers should show no deleterious effects. When these strengths are considered to those of high-temperature steel alloys on a structural efficiency basis, they compare quite favorably. Structural efficiency is strength divided by density, or weight per unit volume, and structural materials are often compared on this basis. There is great significance here, and it can be easily illustrated. Each pound of structural material which is used in a space capsule must be lifted into orbit. And therefore, strength at low weight is very much more important than strength alone. It is a measure of the merit of a particular material. Several methods of fabricating composites are used. The very simplest, of course, is the simple molding technique, and this is used for both plastics and metal matrix materials. For larger specimens and for finished structural components, other ingenious methods have to be used. We see here a square-faced or flat-faced mandrel in which filaments have been wound parallel and adjacent to one another to form a single layer of filaments. These layers can then be stripped off to form tape, or short panels with one layer of thickness. Another method which is used to form composite materials is a filament winding technique, and it is similar in a way. This pipe was formed by a filament winding procedure. In this process, the single filaments, which we saw on the flat face mandrel, can be wound at angles to the axis or perpendicular to the axis in such a way that we provide strength in either the circumferential or axial direction to a desired quantity. By building up the layers in this way, a pipe or cylinder having specific strengths in each direction can be obtained. Pipe formed in this way can be joined in much the same manner as steel pipe with elbows or bolted flanges as illustrated here. Note that the fittings are also filament wound to provide added strength in the regions of highest stress. Besides having strength and weight advantages, the reinforced plastic pipe is extremely corrosion resistant. This makes it an ideal material for use in construction of chemical processing equipment. In a corrosive environment, it has been established that composite materials can outperform metals in many process components. These include tanks, ducts, hoods, and pipes of assorted shapes and sizes. To resist degradation, even the supporting structural members, like this angle section, can be made from composite materials. Here is a set of exhaust fan housings installed in an electric storage battery manufacturing plant. The left fan housing is made from glass polyester. The fan at the right has a steel housing and a stack which has had to be recoated several times because of attack from sulfuric acid fumes. The glass polyester housing has proven its value in this application by reducing maintenance costs. Some of these larger structures used in the chemical processing industry are fabricated by impregnating reinforced fabric with resin and wrapping on a form or mandrel. The reinforcing fabrics are woven from high-strength filaments, such as glass and, in some instances, carbon. After the resin-impregnated fabric is formed to the desired shape, it is cured at optimum temperatures to harden the resin and bonded to the fabric. Large stacks and tanks are often constructed of these materials. Here is such a stack. Sections like this have been joined to erect a stack 150 feet in height. In a unique fabrication technique, a reinforced plastic silo has been constructed from the top down, so to speak. First, the top section is assembled on the ground. This section is then raised as another section is attached from beneath. As each segment is added, the silo is jacked up higher until it is completed, as shown in the photograph at the right. This procedure is made possible because of the lightweight and durability of the material. Another method which is used quite often involves the use of tape. Here we have a piece of tape in which boron filaments have been placed in epoxy in a parallel arrangement. Tape of this kind can then be used in a machine which very simply looks like this. Notice here that tape is being laid by a roller head. The spool of tape is placed here and feeds to the roller. The roller then presses the tape down on the workpiece, and the direction of travel can be determined either by rotating the workpiece or by rotating the tape head itself. Whatever technique we use to fabricate composites, the building of composites is a building up process rather than a cutting away process which we use in conventional metals. There is another method which is peculiar to metal composites, and it is called a zone refining technique. In this technique, we actually form right in the matrix very fine pieces of material, particles, which in this instance are needle-shaped, and this is a cross-sectional view of those needles. These are aluminum nitride needles in an aluminum matrix material. And the magnification here is somewhere on the order of 4,000 times actual size. So you can see that these precipitated particles are much smaller than the whiskers or the boron filaments which we have shown in previous cross-sections. Because of the directional strength and stiffness characteristics of composites, the design for composites is a good deal different from that for ordinary metals. we must first decide on specific properties which uniaxial specimens should have, and then by building unidirectional composites or layers of material which have all the filaments aligned in one direction, we can combine these layers in different orientations to form a complex shape to perform a particular structural function. I think you will agree now that these materials hold a good deal of promise for the future. But the free development of this promise is going to require a good deal of planning and technology. Composites offer a challenge to material science which has already helped to solve such difficult problems as the searing heat of re-entry of a space capsule. I'm sure the future will hold many new problems to solve. However, it will also bring with it the opportunity for applying the principles we have just discussed.
We have been talking about the development and fabrication of these advanced composite materials. Now let's go to Bob Pinckney at Boeing Vertol, maker of large helicopters for the armed forces, to see how they are actually applying these materials to advanced rotors.
Well, we're all familiar with the impact which new design has in our way of life, but the potential impact of entirely new materials is even greater. They make possible completely new products, tools, instruments, even food, medicines, and clothing. Without aluminum, for instance, there would be no jet airplanes. Without iron or steel, we would still be cooking in stone dishes. Similarly, without composite materials, the future of aviation would not be as bright as it is today. At Boeing, for instance, we're building a series of new helicopter rotor blades, made possible by the availability of the new composites. Let's look at the new design and fabrication techniques as they're applied to a rotor blade. And perhaps the examples you see will give you some ideas for application in your own areas of special interest. The first advantage of composite materials is a relative ease with which complex linear shapes can be made. Here are three different rotor blades. The lower two are of a constant airfoil, or a constant shape, a constant width, using roll-form steel or aluminum and laminated glass fiber materials. They are among the best rotor blades in the world today and will perform well up to about 10,000 feet altitude and about 150 miles per hour. However, we're approaching the limit for this type of blade design. The advanced composite rotor blade is the big fellow on top. This is the one in which each airfoil section along the blade has been designed for maximum efficiency in its own particular speed and turbulence environment. The tip or the outboard end is very thin because tip speeds approach supersonic speed. At the same time, the inboard or root end is quite thick, like the wings on a small airplane, to get good lift or vertical thrust at slow speeds. Even though the blade is much larger, about 1 1/2 times the area of the others, it is only about 20 pounds or 7% heavier, and thus it can be flown on an existing helicopter without extensive structural redesign of the rest of the aircraft. Moreover, these new materials offer several other advantages besides stiffness and weight. They have excellent resistance to weather and corrosion, and to battle damage, as you saw earlier in this same sandwich beam. As a result, much less maintenance will be required in service. Because the blades are composed of strong fibers held together by a more elastic matrix of resin, they have excellent resistance to repeated bending and fatigue. Here we see that damaged boron beam clamped to a similar beam of fiberglass. Notice how much more stiff the boron beam is compared to the glass fiber reinforced beam on the lower surface. All of these factors make us believe that we can achieve a useful life 5 to 10 times greater with the new materials than those of our current products. Now let's take a look at the actual construction of such a component being built at our Wichita plant. We are molding the new materials in much the same manner you would make a model from clay. That is, by the controlled application of pressure and temperature. Since these materials are very stiff in one direction and very pliable in the others before curing, we must use fluid or uniform pressure techniques and a precisely shaped mold. Here is a Spar Mandrel, as it is called, simply a strong, elastic, shaped rubber balloon upon which the pre-preg is placed according to the design requirements for weight and stiffness. The boron epoxy tapes in this case are aligned parallel to the load or force which they will eventually have to resist. As a result, many of the filament reinforced tapes go from one end of the blade to the tip and return in a continuous piece. This serves to resist centrifugal loads and flapping or bending moments. Fibers are added in other directions, such as at plus and minus 45 degrees to the blade chord, in order to control the torsional stiffness or twisting resistance. Once all of the fibers have been positioned and tacked in place, an outer form or mold is put over the layup and bolted together. Pressure is then applied in an autoclave to compact the materials. This machine looks complicated, but actually it is just a big pressure cooker containing its own heat source. A final composite cover skin is molded and bonded to the structure to complete the blade. A tool called a bonding fixture is used to hold the previously cured components into position during the final bonding operation. Again, the principle of heat and fluid pressure is used to cure the materials in their final form. At the present time, much of this work is being done in hand layup, individual ply operations. The future holds opportunity, perhaps for your company to design tape laying machines and automatic control equipment to do this work.
We've covered the highlights of some of the work of engineers and scientists in the nation's laboratories and factories. It won't be long before you'll be able to ride in aircraft which are made at least partially of these new materials. However, though our illustrations have been drawn from the aircraft industry, we must not leave you with the impression that the elastic behavior and strength are the only properties of interest in these new materials. Indeed, it is already clear that the electronic, the optical, and the thermal properties of these composites can also be exploited, yielding new instruments, semiconductors, and prosthetic devices, for example. Thus, it is entirely possible that an early application will be in dental appliances. We hope we've aroused your curiosity and your interest in what this new era of composite materials may bring forth. If you are yourself engaged in any industry dealing with materials and design, a great many potential applications may occur to you. If you'd like additional information, we invite you to write to PENNTAP.
For more information about PENNTAP, write 201 Wagner Building, University Park, Pennsylvania, 16802. Looking at Materials is produced for the Pennsylvania Technical Assistance Program with funds provided by the Federal and Commonwealth Departments of Commerce under the Federal State Technical Services Act of 1965.